Hello and welcome to this online presentation. I am going to present you a work that we did with Hugo Herbelin about the definition of well-typed continuation and environment passing style translations. And to that end we had to introduce the new calculus, a calculus of expandable stores, and this is what I'm going to present right now. I assume that anyone listening to this talk is already very familiar with the lambda calculus, of which you may know that this is a very nice abstraction, nice computational models with many expected properties, and in particular it has different evaluation strategies. There are different ways of computing things, and you may also know, I assume, that these different evaluation strategies can be specified through abstract machines, so there exists a huge variety of abstract machines. And one nice thing about this is that if we want to reason about abstract machines within the lambda calculus, there exists a wonderful tool to abstract this notion, to reify it, which are continuation passing style translations, also called CEPS, because they are internalizing somehow the operational semantics within the lambda calculus through a translation that is also specifying an evaluation strategy, also making explicit the control flow. And in addition to that, since they also induce a type translation, a translation at the level of types, not only for terms, we can see typed continuation passing style translations as syntactic models insofar as they allow to transfer logical properties like soundness or normalization from the target calculus to the source calculus. Among the different evaluation strategies of the lambda calculus, you may know the lazy evaluation, also called call by need. Call by need, just like in call by name, evaluates argument of functions only if they are needed. So we don't do useless computations, and more than that, as in call by value, when something has been computed, the evaluation, the value, is shared across all the places where it is needed. So it's in some sense it is a mix of call by name and call by value. And to put it in a nutshell, call by name is just daemon-driven computations. So you compute when you need it, plus a memorization technique to avoid recomputing arguments of functions. This evaluation strategy has many benefits. In particular, it is used in well-known computational systems like Haskell, Coq. So in Haskell, for instance, it is the default evaluation strategy, and in Coq you can use it as a tactic, but it is also present already in the kernel. Nonetheless, it has been less studied historically than call by name and call by value, and it is trickier for many reasons that we will see. One of these reasons is that if we consider the usual abstract machines for the lambda calculus, so for instance here the Krivin abstract machines of call by name, it uses local environments and closures. So the terms here is computed in front of a stack and within an environment, and we can see that when we push, for instance, an argument onto the stack, we are copying the environment to form a closure here of U with the current environment. And when we pop an argument of the stack, so for instance to apply the beta reduction rule, we are linking U with the closure U with its environment. So we are copying many environments, and they are local but into closures. Obviously this is incompatible with lazy evaluation insofar as we want to share computations, so we need global environments. So this is, for instance, the case of the Milner's abstract machine. So also for the call by name evaluation strategy here, we can see that the term is computed in front of a stack together with one global environment which is not copied. So when we push onto the stack, we don't do any copy. When we abstract, when we perform the beta reduction rule here, we get U, and we put the link X to U once in the environment, and the environment of U is given by the prefix of the environment here. And one difficulty is that when we have a global environment, we need to explicitly say how we address the issues related to names. So one solution is to say that each time that we get a term out of the environment, we have to get a fresh copy with fresh names, because otherwise T may be putting new terms into the store here into the environment, but if the variables that are going to be put afterwards are already present, we are going to have some name clashes potentially. But more than these difficulties that are somehow already handled, because we know how to define abstract machines with global environments, and there exist also by need abstract machines. The hard question is to know how to define some CPS translation, and actually a typed CPS translation, but already untyped is a hard question, because it can not only be a continuation passing style translation, but it has to pass somehow the environment, because the environment is global, so it has to be passed around during the computations. And for that, there are several difficulties to handle. The first one is to understand how the control and the environment should interact. So how to define, for instance, a classical calculus with lazy evaluation. This is already done. I will explain this afterwards. But what wasn't known when we started this was to know how to soundly type environments, and in particular how to type them along the translation, while accounting for extensibility, because environments may grow along computations, and we need to have a type system which is going to account for that, and also how to have a technique to avoid name clashes, which is especially tricky during the translation. In this paper, we are precisely defining well-typed continuation and environment passing style, which I will call CEPS afterwards. And our main contribution is the introduction of a calculus, F epsilon, which is generic as a target for CPS translations. This calculus, as we will see, is featuring two main things. The first one is the type for typed stores, and the other one is a mechanism of explicit coercions, which is going to witness the extensions of stores. Why do we call it generic? Because our goal was not only to define well-typed CPS translations, but also to isolate the key ingredients necessary to these definitions. And as we will see, we can indeed use F epsilon to define CPS translations for different calculi. At least in the paper we do it for 3 calculi, simply typed called by need, called by name, and called by value lambda calculus. And we shall discuss the possibility of using it for more involved type systems, so for instance system F as an input. What are continuation and environment passing style translations? Actually, the very first question to answer is to understand how to define a correct operational semantics of a calculus with control operators and shared memory. Indeed, to define a CPS translation is usually equivalent to define the operational semantics of a calculus with control operator. And these questions is actually very hard, and it was already tackled in 93 by Okazaki, Lee, and Arditi. And you can pause the video if you want to look in details at this example, but they had the semantics saying that what is not forcing an effect, so what is not reaching a catch or throw operation, shouldn't be shared. So this is wrong. I'm saying something wrong. Blah blah blah. In order to define a CEPS translation, the very first question to answer is to understand how should be the correct semantics of a control operator, so the mechanism related to continuation passing style, in presence of shared memory. This question is hard, and it was already tackled in 93 by Okazaki, Lee, and Arditi. You can pause the video if you want to look at the code example which is on the left. But in their semantics, they were saying that what is not forcing an effect, so what is not leading to a throw, has to be shared. So in particular, in this example, F and Q, Q is shared and F is recomputed. And in the end, if you look at this very particular example, it is going to loop. while it shouldn't. And so their semantic wasn't correct, and that was shown later by Ariola and several others. And in turn, they propose a semantic in which nothing is shared inside an effect. So in this example, F and Q are recomputed, and indeed this code piece is going to reduce correctly to the pair of identity. What was their method? In the paper, they defined a sequence calculus for a classical call-by-need calculus, and then they derive from the sequence calculus an abstract machine, and then from the abstract machine they derive an n-type CPS translation. This is known as the method of d'envie semantic artifacts. And we show in a previous paper also with Hugo Herbelin that their semantics can be typed normal and that it is normalizing and consistent. And to that end we use the realizability interpretation. What are the intuitions that we can get from previous works? Well, if we look at the sequence calculus defined in the paper of Ariola et al., we can see that the sequence calculus has three components. We have a term which is evaluated in front of a context, as is usual in sequence calculus, plus an external environment, as we had in the abstract machine with global environments in the beginning. So I'll let you pause the video if you want to look closer at the syntax, but in broad lines it has three categories for terms, context, and environments. And the categories for terms and context are divided into the notion of terms, the notion of weak values, and the notion of strong values. And we have the corresponding notion for context, so usual context and co-values and strong co-values if you want. And you can think of these three syntactic categories as the categories needed for the interaction defined by the lazy evaluation. We have less when we have call by name or call by value, and we need more because of the lazy evaluation. If you look at the reduction rule, just to see that this is indeed lazy evaluation, we can see that here when we have t in front of mu tilde x can be read as let x be t in C. Then what we do is we store lazily t together with the variable x here. And if at some point we need the variable x, we need its value in front of a demanding, a forcing context here, and that x has been linked with the term t, we are going to freeze the computation here, open the store and do the computation for t. And if t eventually produces a value here, a value v, then we put back x together with the value v, and we go on with the computation now where x has been substituted by v. So this is really lazy. We lazily store, and if really we need it, then we do the computation, and once we've done it, it is done for forever. Okay, so this is lazy evaluation. What about the untyped CEPS defined? Well, as we can imagine, it has an extra component. It has not only the component for continuation passing, the continuation passing part, but also something which is the environment passing part. And again, if you want really to look at the details, but it's not necessary, you can pause the video. But what is important to see here is that we have everywhere a blue and a red part corresponding to the environment passing part and the continuation passing part. Okay, so the translation of a term or context is going to be something waiting for a store, and then waiting for a term or continuation, and then producing the computation. The second step consists in defining the type translation corresponding to the environment passing part. And to that end, let me give a bit of intuition. So in a sequence, if we think of what is the role that the context plays, actually we can think of the context as a specification for correct substitution to get t of the corresponding type A here. So gamma is saying what should be the type of variables, and actually the environments that we are handling in the CPS and in the sequence calculus, there are some kind of explicit substitution. So the type of the explicit substitution should be the type of context, and saying that t is of type A under the context gamma is saying that t is waiting for a substitution of type gamma, so the translation of gamma here, to return a term of type the translation of A. So let us write this translation here with this new notation, and the index t is saying that we are translating at the level of term rather than context value and so on and so on. So if we unfold, t is waiting for substitution and environment of type gamma, and then a continuation of type a under the translation corresponding to the context gamma, and then returning bottom because of the continuation passing part. And again, if we translate here, if we unfold the definition of the translation at the level E, then we are going to get this this definition. So the continuation is itself waiting for substitution of type the translation of gamma, waiting for a value, and then returning bottom, and so on and so on. And we can define the translation for the 6 layers here. And again, we can see clearly the fact that we are waiting for an environment and using a continuation in the end. The next step has to do with the fact that the environment can grow. Indeed, look at this possible reduction scheme. So assume that we have a computation in which we are needing the value for x, and x has been linked to t in the environment. What do? We are freezing the computation for the moment, then computing the value of t in the prefix of the store, because the store has been split into 2 parts. Then t is eventually going to produce a value, and if it does, we are going to put it back into the store. But while it was computing, t may have been adding some new elements here to the store, so in the end we get a store that has been extended. And of course, this is actually a bit more complex than that. It could be recursively at any place in t1 and t2. So the store might grow at any time, at any place. The key idea is that, just like we were saying that the translation of gamma it was specifying what are the correct substitutions, our idea is to say that any substitution that contain at least gamma should be considered correct, meaning that if t is of type the translation of a under the context gamma, it should be compatible with any extension of the whose type is an extension of the translation of gamma. To that end, we introduce a notion of store subtyping, which is really easy, the natural one, saying that gamma prime here, this one is an extension of a1, a2, because we have a way to find a1 and a2 both in the extension of the store in gamma prime here. About the translation, so with that at that stage we were using this definition, and now we no longer want t to be waiting for a store of type gamma, but any store of whose type is an extension of gamma here. And again, this has to be defined recursively, so the continuation itself is waiting for an extension of that store actually, and we can define the translation at the 6 layers. The next and the last step is to understand how to avoid name clashes, and this is actually really important because in the previous work of Ariel et al., they were implicitly relying on the possibility of using a non-deploy process of alpha renaming, and while this is perfectly fine with the sequence calculus, this is actually incompatible with the CEPS translation. Here, in turns, we will use Debrun levels, both in the source and the target. So in the source, it means that the name here is actually n rather than x. This is in hybrid notation, and the n is referring to the position both here in the typing context, because we saw that the context is the type of the substitution of the environment, and to the type of the position, the position in the store here. And we can see that when we are looking for xn, we look at the nth position into the store, and if, as we saw before, we want to store back a value v, but some extra element have been added to the store, so there is a mismatch between this level here, I and n, and then we have to explicitly say how we lift the mismatching Debrun levels. In the target, we simply drop the names, so we no longer use neither this hybrid notation, neither levels, and we just say that t is of type the translation in the context A, B, C here. And we use coercions to witness store extensions. So coercions, they are simply functions saying how we can follow the extension to find the expected competence. So if we are looking at the first position, we were expecting something of type A1, the coercion sigma is going to help us to find it into the extension. So we've seen how we can hope to type a CEPS translation, and now we can present you the calculus we define, F epsilon, that has all the necessary features to define such translation. Remember that our wish was to define a calculus, a parametric calculus, to serve as a target for different CEPS translations. Each of the CEPS translations we will see can be divided into 3 blocks. The first one is the source calculus together with its type system. So here we will only present simply typed calculi, or at least in the paper that's what is done. Then we need the syntax to handle stores and coercions, and afterwards the target calculus, which is going to use the 2 first block, and it's going to be an instance of what we call F epsilon. In the paper we only use lists to represent store, but we could also imagine to use trees or whatsoever. And so we can see that both store types are defined as list of types, while stores are defined as lists. So we have the empty list, the list extended with one element, and the concatenation. And we have typing rules to say that to here is of type epsilon if it is appended to a store whose type is epsilon prime. We can see that, for instance, in the concatenation rule here, we need to take into account for the second component the store of the first component here. And also, if the type of a store is always a list of source types, the way these types are translated here is a parameter of the target. So we can see that when we have one element, it is of type T here, under the context epsilon 0, if the term T is itself of the type here, this black triangle, which is going to be a parameter which will instantiate with precisely the type translation of the expected, the desired CEPS. What about coercions? Well, they are the proof terms witnessing list inclusion. So we have the base case. We have a case for saying that we are adding the same type in both sides of the list inclusion, and we have the case of a strict extension. So we say that this is an extension here of epsilon if we have been adding something, and that the prefix epsilon prime is already an extension of epsilon. So for instance, you can pause the video if you want to look at this example, but here we have the proof term witnessing the extension of TU, T0, TU, T1, and if it can be helpful, you can think of this witness as something corresponding to the function which maps the Debrun levels, the position in the store 0 to 1, 1 to 2, 1 to 2 to 4 here. So what is system F epsilon? In broad lines, this is just system F extended with stores and coercions, and actually this is a bit more involved than that, but this is the good idea I think to have in mind. As for the syntax, we have the syntax for store types, for stores and for coercions that we saw, and then the lambda calculus. So we have here something which corresponds to the source calculus. Here it's simply typed, so we only have base case and functions. Terms to abstract coercions here and to apply to coercions, the same for stores, the same here for store type, and one extra important term, which is the one explaining us how to, giving us the ability of cutting a store. So intuitively, split here is used to look into a store of type epsilon prime, which is the store tau here, for the term that was expected in what epsilon prime is extending at position n here, using the coercion. So we were expecting here a store of type epsilon, we were looking at the nth position, and we are actually giving with the store tau, whose type is an extension of epsilon, and what split is doing is looking through the coercion to get the expected term and splitting the corresponding store into 3 blocks. We have three kinds of reduction rules. We have the rule for split that we just saw, the rule for normalizing coercions, because we need to abstract over variables for store types and so on, so it's a bit more complicated than what I saw, but this is the same idea. And the usual beta reduction for abstractions and applications, and we can show that the reduction we define is preserving the typing of the system, and that type term can be shown to be normalizing. Also, if you want to have a look at the system, we define a shallow embedding in coq of f epsilon, and you can look at this definition and see that they are really what we are showing here. As an example, we show in the paper that we can take advantage of the genericity of our definition to define different CPS translations. So remember that here, to define the type of a term into the store, we are using a parameter that we can choose depending on which translation we want. And indeed in the paper we define well-typed CPS using this for call by need, call by name, and call by value, and the only thing we have to do is to change, of course, the translation of terms, and here change the parameter to use the correct translation for types. All these translations follow exactly the intuitions we saw before, so we have a continuation passing part mixed with an environment passing part, and the environment passing part is corresponding somehow to a crypto style forcing. And we discuss in the paper the possibility of extending and we discuss in the paper the possibility of considering different inputs, so no longer simply type calculus, but for instance system F, and this should be okay just by using the usual forcing translation for system F. To conclude, we believe that we managed to isolate the key ingredients to define well-typed CEPS. So the first thing is to have terms to represent and manipulate type stores, and the other one is to have a mechanism of explicit coercions. Then we show that our calculus, our proposition f epsilon, has the benefits of being really parametric. We can use it for different CPS, we can use it with different source type systems, and also we don't know if that can be of any use. We can use it with different implementation of stores. From a logical point of view, we've seen that CPS amounts to some Kripke forcing translation interleaved with a negative translation, and actually the connection with Kripke forcing or with forcing in general does not come as a surprise, because it was already done that both forcing and the state monad, for instance, can be given a semantic through presheaves. And also it is worth mentioning the work of Krivin to simulate forcing in classical realizability, and he uses an extra cell, so somehow state monads. A few open questions for the work. The first one is that we believe that this may constitute the first step towards the definition of well-typed compilation processes for calculi in call by need. Also, we would like to know what is the exact expressiveness of f epsilon, because we said that it was broadly f plus store types and subtyping relation, but actually it's a bit more than that, because we have some sized types, so we need at least a slight bit of dependent types, but of course this is way less than the usual type theory. Finally, we would like to see whether we could define the type translation through a modality. By this we mean that if we look at what is the translation of A under some contexts, this function is mapping a store type here to a type, and what we've been doing all the time is to use the transformation on such function, saying that if f is such a function, we consider the function mapping a store type to the whole translation, that is waiting for an extension, getting a store of that type, then using f to transform this extension and returning bottom for the continuation. And then with this definition we can see that the translation at the level A is the box of the translation at the level E, and this is itself the box of the translation at the level V. Just like in a usual CPS translation, we would have the box being a negation and then having a negation here alone. So we would like to see if, just like the negation again, this box may have some interesting logical properties. Thank you for your attention, and of course we would be happy to answer any of your questions either at the dedicated slot at LICS or by simply sending us an email, and we will be happy to answer. Thanks.